So sample problem 4.6 brings in our concept of balanced molecular, total ionic, and net ionic equations in the context of acid-base reactions. So again, we've already learned about molecular, total ionic, and net ionic equations with precipitation reactions, so now we're just going to apply this to acid-base reactions. And what I hope you see is that acid-base reactions are really just another kind of those double displacement reactions where we actually swap partners. And when we swap an H plus for an OH minus, that makes water. So again, these acid-base reactions make salts and waters through that double displacement chemistry. So as I kind of was indicating when we learned about our total ionic equation, I want you to get to the point where you can kind of mentally see our total ionic equation, because it becomes a challenge if you can only get to the net ionic equation if you have to physically write out the total ionic. It takes a lot of time to write out that equation, and the more quickly you can get to seeing that mentally will save you a lot of time as we work through quizzes and exams. So we've got 3 problems to work through. Again, with each of these problems, I'm going to highlight something that's unique to it, why it's not just doing 3 of the exact same problems, why there's 3 of them there, and what's unique, and why we spend time working on 3 separate ones. Again, Chapter 2 skill, really important here, being able to translate a name into a chemical formula. So in this first problem, we've got HCl reacting with KOH, and when we give reactions with names, they're certainly not balanced, so we'll have to make sure we consider balancing chemical equations here. As I mentioned before, I want us to think about acid-base reactions like we thought of with precipitation reactions, swap partners. So H plus is going to find a new partner in OH minus, and K plus is going to find a new partner with Cl minus. Okay, and so that's how we get HOH, which is again water. Okay, and then we get KCl. We can't forget our precipitation chemistry because the new ionic compound that we make might be a salt that's not soluble. So we need to refer to table 4.1, and in that case we see that all potassium salts are soluble, and so we know that this is an aqueous problem. Again, making our total ionic equation, I'm going to try to just kind of mentally go from our molecular equation to our net ionic to see if we can do that. Kind of get away from having to physically write out our total ionic equation. I want us to think about this mentally. All right, anything that's on the left-hand side is going to be aqueous as our ions. That's what we start with, is aqueous solutions. So then we need to look and compare and see, is it the same on the right? So for example, I look at H plus over here, that would be aqueous. It's not H plus over here. So that means H plus is going to be part of my net ionic equation. It's not a spectator ion. Chloride, Cl minus over here. As part of a soluble salt over here, Cl minus would be a spectator ion. Okay, so maybe I'll just kind of write over here, these are my spectators. So Cl minus is going to be a spectator ion because it's present as a chloride aqueous form on the left, and since we know this is aqueous, on the right. K plus aqueous on the left, K plus aqueous on the right, so K plus would be another spectator ion. OH minus on the left, we don't have OH minus on the right, so that is not a spectator ion. That becomes part of our net ionic equation. Similarly, anything that was on the left-hand side of our net ionic equation has to make something different on the right side. So that's how we make our net ionic equation, and do it mentally by thinking about who our spectators are on. So again, we thought about this mentally. Okay, this problem is a pretty straightforward acid-base problem. It's what I call easy because the stoichiometry is 1-to-1. What we'll see as we work through B is it's not 1-to-1 stoichiometry, and that's what makes that problem different. All right, strontium hydroxide. Strontium is an alkaline earth metal, so it's going to have a charge of 2+. So strontium 2+ mixing with hydroxide is going to be SrOH2. We know it's an aqueous solution to start. Perchloric acid, HClO4. Again, if you have a hard time remembering that that's perchloric acid, go back and review acid nomenclature from Chapter 2. Okay, right now I can automatically see that I've got 2 hydroxides coming here. Perchloric acid is another one of those monoprotic acids. So I know I'm going to need 2 of them in order to react with the 2 hydroxides that I have here. These acids and bases react, again giving us new partners. We're going to have H going with OH minus, SR going with ClO4. So we're going to make HOH, we're going to make our water. Because I already knew ahead of time I was going to have to balance that, we're going to get 2 waters. And then strontium is going to go with 2 of our perchlorates. But again, we need to refer to table 4.1 to see whether this species is soluble. And again, I'm not going to show that on this problem. Review your precipitation chemistry if you need help on how to use table 4.1, but this is again a soluble salt. Mentally, let's go through and see if we can identify our spectator ions. Strontium on the right as an aqueous ion, strontium on the left. Not going to be, left and then right. Not going to be part of our net ionic equation. Our spectators are going to be strontium 2+. Hydroxide, not the same on the left as the right, so that's going to be part of our net ionic equation. I'm going to have 2 of them coming from this guy. Again, protons, going to be part of our net ionic equation here because they're part as water over here. Perchlorate is found as perchlorate over on the other side as well. So that's going to be another spectator, not part of our net ionic equation. And so water is again also part of our net ionic equation. So you can see that the net ionic equation is the same for both of these. But what makes this problem unique and different is that there is a 2 to 1 stoichiometry. Our strontium hydroxide brings 2 hydroxide ions where our perchloric acid is only a monoprotic acid. So we have to have 2 of them there. All right, our last problem is going to introduce a third thing that we have to think about when we're doing our acid-base chemistry. And again, if you think about this as a swapping partners, always remembering that we have to consider the salt solubility. You won't forget to do what we have to do in our next problem. All right, barium hydroxide. Barium is 2+, which means we need 2 hydroxides with it. Starts out aqueous, sulfuric acid. Sulfuric acid, one of our strong acids that we need to know. We can already see that this is a diprotic acid. It's a strong diprotic acid, so each of these protons is going to go with our OHs, and then again for our barium, that's going to go with sulfate. So we can make 2 waters, but again, I don't need to change the coefficients up here because it came as a diprotic acid. And then we're going to have barium sulfate, but again, I need to refer to table 4.1. And we can see from table 4.1 that this is going to be a precipitate. All right, going ahead and mentally looking at what we might have here. Barium is part of a solid compound on the right, started out as an ion, so that must be part of our net ionic equation. We know that this is acid-base chemistry, so hydroxide is going to be part of our net ionic equation. Similarly, we know that our protons are going to be part of our net ionic equation. Because sulfate is forming a solid precipitate here, sulfate must be part of our net ionic equation. And water and then barium sulfate are what we get from those ions. So what's unique about this guy is there are no spectator ions that are present. So our net ionic would actually be the same as our total ionic. So the total ionic would be equal to the net ionic. And again, that's because there are no spectator ions. So again, 3 different acid-base reaction problems. Try to get to the point where you don't need to write out the total ionic equation. I'll tell you, I'm not going to ask you for the total ionic equation on quizzes or exams. They take a lot of time to write, and you're better off learning how to see that mentally so you can get directly to your net ionic equations.